boxes, head goes in next. I've got memories and travel like a thief in the night. And I've been tired, I've seen this road 1,000 times. I've got no roots, but my home was never on the ground. I've got no roots, but my home was never on the ground. I got no roots. Good morning, everybody. This is not normal for us to go through 3 songs in our class because we were here so early. All right, let's go ahead and take a look at our first diagram. Which diagram is used for using the right-hand rule? Remember, the right-hand rule is to use your right hand. Thumbs up, everybody. And we look at this particular diagram and we try to find which way the current is going. That's going to point us in the direction of our thumb. So with that being said, we're going to look at this diagram and we're going to notice that yes, the current is going down. So that means our thumb, thumbs up, thumbs down. So now we're going to ask ourselves, how do we wrap our hands around that? If our thumb is down, are we going to the left? Are we going to the right? And if you think about it, we can't go to the right because then we bend our hand back, we're actually going to the left. And so that, yes, I agree with everyone right there. And yes, this is the correct answer right here. Let me grab my tool. Whoop. There we go. This is the correct answer. So excellent job, everybody. Let's go ahead and flip gears and talk a little bit about food. Of course, when we're so close to lunch, what are we trying to do to you? So what is your favorite holiday food? Cranberry sauce. And then after the holidays, you could make some turkey sandwiches and put the cranberry sauce in, like mayonnaise. Oh, it's so good. So good. Turkey and cake, mac and cheese, pumpkin pie, all these sound so good. And if you have a favorite food, let me know in the chat box. I know for us, I make tamales usually in December, early December, I make tamales. And so, again, it's quite an undertaking and it's pretty hard. Oh my gosh, you've been able to eat pure cranberries before. It's great on turkey stuff. Yeah, I agree with you, Rowan. Absolutely, 100%. Yeah, I don't like mayonnaise either, Antoine. Ugh, I don't like mayonnaise. No way. So let's go ahead and continue on. Here we go. Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box for your protection and the protection of others. Be respectful and always participate. You know that one. That's a good one for us. All right, let's go ahead and look at, we are in week 12 of 13. We're at the point of, we're being a week and a half away from ending our Try 1. And me and Mrs. Larkin are definitely going to miss you all. It is 6 days left. I cannot believe it. Unless you're joining us for chemistry, then we get to see you again. It is Wednesday, November 4th, and we're going to talk about magnetism causing electricity, and we're going to talk about doing this with our 5H assignment and our 5H attendance discussion. Just a friendly reminder, make sure you're sticking around till the end of class to get that 5H attendance discussion answer and that we discuss. And then obviously, if you are putting anything weird or bogus in the attendance discussion, we are just simply just kicking it back to you. It is kind of a waste of our time and a waste of your time in essence, so just kind of be aware. Stick around, get that attendance prompt, get full credit. All right, so let's go ahead and talk about what we're going to talk about today. Identify an induced field of loop depending on the motion of a magnet. Use the right-hand rule to determine the direction of the induced current, and we're going to do this all through our 5H assignment. And you know what I'm going to say next slide, so I'm going to go ahead and already get that popped up in there. Some of you already have used Shinkansen speed and gotten your notes already open, so there it is up in the slides. I'm going to go ahead and place it up here on the board, and then obviously if none of these work for you, you can always find it in your grades tab. So 3 places for you to find this. There you go. I'm going to give you about 25 seconds to get you locked in. Again, if we don't hear from you, if you're not working quickly and properly, then we will move you into the check-in room to make sure that you are okay and kind of check in with you. So let's get that going. Open up your assignments. 3 places. Go, go, go. Check in with a few people here. We need, yeah, exactly, Daniel. We need some Ben Franklins up on the board here. Let's go ahead and check in. Annabelle, Annabelle, green check. Andres, Andres, green check. Let's get those up there. Chad, 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 green check. Looking for Haley, Haley, green check. Ivana, green check. Again, if you're having issues or if it's your computer's acting slow, just let us know in the chat box so then we know that you are with us, that you're not just walking away from your computer. Matthew, Matthew, green check. Looking for a green check from, that's it. Let's get those green checks in. Looking for a green check from Chad, Chad, Chad. Last chance, Chad. Green check, please. Green check, Chad. All righty. Let's get a green check from Ivana. Ivana, green check, please. Ivana, green check. Last chance, Ivana. Oh, there you go. Thank you so much, Ivana. All righty. And Matthew, Matthew, last chance. Matthew, green check, please. Matthew, green check. Green check. All right, perfect. All right, let's go ahead and move on to our brainstorm.
Perfect. So let's go ahead and take a look at this at these problems here. So let's imagine that we have two magnets and we want to keep magnet 1 from moving. And so we need to figure out what should magnet 2 be in order to keep magnet 1 from moving. So let's take a look here. In this instance, magnet 1 is trying to move to the right. It's trying to get closer to magnet 2. So what do you think magnet 2 wants to do to keep it from moving, to keep it from getting closer? Do you think it wants to attract it or repel it? If a magnet is coming towards magnet 2 and magnet 2 doesn't want that to happen, what should magnet 2 do? Attract it or repel it? Attract it or repel it? Think about if you have a stranger coming towards you and you don't want them to come towards you, what do? Do you want to attract them or repel them? Awesome. I see Lisa, I see Antoine, I see Steven, Sally in the chat box. No, your only options, Antoine, are attract or repel. Attract or repel. Yeah, so if you say go away, Stephen, right, that would be repelling. Perfect. So in this instance, we want to actually repel. We want them to go away, go away. All right, so if that is the case, then what should this pole of magnet 2 be in order to repel magnet 1? Magnet 2 wants to push away, so what should that pole be? What pole is going to repel a north pole? What pole is going to repel a north pole? Awesome. I see Stephen, Antoine, Regine, Lisa, Rowan participating. Yeah, remember, likes repel. So if we have a north pole, then the like pole should repel it. So what is that like pole? Thank you, Andres. Thank you, Sally. What is that like pole going to be? Yep, it's going to be a north pole. So that'll be our north pole, and obviously the other side will be the south pole. Great. Now this time, let's imagine that the magnet is trying to move away from magnet 2. And magnet 2 does not want this. So what should magnet 2 do? Should it try to attract it or repel it? If magnet 1 is trying to go away, does magnet 2 want to attract it or repel it? This is like if someone you like is trying to walk away, what do you want to do? Attract them or repel them? Attract them or repel them? Awesome. I see Rowan, I see Greta, Stephen, Lisa. Yeah, magnet 2 can't make up its mind. So here we go. Magnet 2 says that it wants to now attract magnet 1. All right, so it wants to pull magnet 1 back towards itself. So how should it do this? If it wants to attract a north pole, what should magnet 2 be on this side? If it wants to attract a north pole, then on this side it should be what? Awesome. Yes, I see Sally, Greta, Antoine, Rowan, Regine participating. Remember, opposites attract. So what is the opposite of the North Pole? Correct, everybody. It's going to be the South Pole, and obviously the other side of our magnet should be the North Pole. Please go ahead and give me a birthday cake in the chat box if you feel comfortable with what we've done so far. And we'll get to why we're doing this in a little bit. There is a reason why we're doing this. Awesome. Let's go ahead and practice what happens if we flip magnet 1.
All right, so let's go ahead and talk about this. If you wanted to prevent magnet 1 from moving to the right, should the poles of magnet 2. So we're saying magnet, or this person wants to come closer, but magnet 2 is like, oh no, I don't want you near me. Is it attracting or repelling? Is it attracting or repelling? It's magnet 2, exactly. Good, good. Let's see if I get this spelled right today. Repelling. Maybe not. All right, so if it is repelling, Yeah, ew, I don't want you near me. If it is repelling, then what is this pole going to be? Is this going to be a north or south pole? Is this going to be a north or south pole? Good. Good. I'm seeing those answers fly up. Beautiful. Yep, I agree. It's going to be a south pole. And then obviously this one would be a north pole. Now looking at the bottom one right here. So if we're looking at the bottom one, and this person or this magnet is walking away, but magnet 2 is like, oh, no, come back. I want you to hang out with me. Is this going to be attracting or repelling? Yeah, the magnet 2, come back. I want to talk to you. Exactly. That would be attracting. Good. So if it's attracting, again, that old saying of opposites attract, would this end of the magnet be a north or a south? Good. Sally's got an answer. Stephen's got an answer up there. Beautiful. Regene's got an answer. Nice. Yes, I agree with you. It is going to be a north, and then this one would be a south. Go ahead and give me a black bat if all of this is making sense. We just kind of did the same thing, but we just switched our poles here, but making sure that we understand this, making sure we understand. Give me a black bat. Excellent. Beautiful. Let's go ahead and move on.
All right, so you're probably like, why are we doing this? There is a reason, all right? And what we're going to see today is that we are going to learn how magnets can actually create electricity. So we already talked about how electricity creates magnets, but today we're going to talk about how magnets can actually do the reverse and create electricity. Okay, so this happens when a magnet tries to move through a loop of wire. What it does is when a magnet tries to move through a loop of wire, either in or out, the loop of wire is going to oppose that motion by creating its own magnetic field. And this is what is called an induced or caused magnetic field. So the loop makes its own magnetic field to try to prevent the magnet from moving. Now remember, this loop is just a plain old loop. It has no electricity, it has no magnetism by itself. The only reason that it gets this magnetic field is because of this moving magnet. All right, so it's just a plain loop of wire. And we'll talk about in a little bit how that magnetic field can then create electricity, because again, that's our final goal, is to figure out how can a magnet create electricity. Now, here we go. If the magnet goes in, then what we just saw is the loop is going to try to repel it away. So this is like if you're being approached, the loop doesn't like that, and so the loop is going to try to repel it away. So this is my example picture. So it's going to create its own north pole to repel it away. Please note that the reason this is in dotted lines is because this is not a physical real magnet. So the loop is creating a real magnetic field, but that magnetic field doesn't physically turn into a magnet. Please give me a smiley face if that makes sense. So this is just representing the magnetic field. Obviously, a real magnet doesn't just appear. A real magnet doesn't just appear. Okay, cool. So here we go. So if the magnet were to try to leave, though, on the other hand, we just practiced this together, then the loop is going to try to do the reverse and attract it back. It's going to say, wait, don't leave. So the loop is a lot like, hey, please don't get closer, but also please don't leave. So whenever the magnet tries to do something, the loop will try to do the opposite, and that induces a magnetic field, again, represented here by an imaginary magnet. Now, here's the thing. What scientists discovered a while ago is that, yes, it's very easy for us to recognize that electricity causes magnetism, but it took them a lot longer to prove the reverse, that magnetism can result in electricity, can cause electricity, because they weren't moving the magnets. So the magnet does, in fact, have to move. If the magnet doesn't move, then the loop doesn't do anything. The loop doesn't try to change anything because the magnet's not doing anything. We're going to learn later, again, that this is related to electricity, and remember that electricity is flowing charges, so it makes sense that the only way those charges are induced to flow is if the magnet itself moves. So in order to have flowing charges, you also have to have a flowing or moving magnet. This is number 1 in your assignment. Go ahead and fill in the first blank with the word repel, the second blank with the word attract, and give me a green check when you have that saved. You have 40 seconds to fill in both of those blanks. Make sure you spell them correctly. If we don't get your green check, we'll go ahead and check in with you. Go, go, go. 20 seconds remaining, and I need about 10 more green checks. 5 seconds. All right, we're waiting on green checks from Bryant, Ivana, Ivana. Green checks, please. Jose, Luis, and Moises. Green checks, please. Just looks like we're waiting on Luis and Moises. Green checks, please. All right, we'll go ahead and check in with Moises. Let's go ahead and move on. All right, let's go ahead and actually practice this together. So if our magnet in both of these instances is trying to leave, we already figured this out. If the magnet is trying to leave, then the loop's induced magnetic field will try to do what? Will it try to attract it back or repel it away? Right? If the magnet is trying to walk away, what's the loop going to do? Try to attract it or repel it? Tell me in the chat box, everybody. Is it going to try to attract it or repel it? If it's trying to leave, do we want to attract them back or repel it away? Think through that question before you answer. There we go. I see Rowan, Lisa, Antoine, Regine. Yes, thank you for correcting your answer, Regine. I see Stephen and Sally. Thank you for correcting your answer. Great job. Yeah, it's going to try to attract it back, right? So the magnet's trying to walk away. The loop's saying, no, wait for me, come back. All right, the loop wants it to come back. So in both of these instances, we want to attract. We want to attract back. Please don't leave us. So if we want to attract it back, then what is this imaginary magnet going to look like? What poles should go here for this imaginary magnet? Again, it's a real magnetic field, but we're just representing it with an imaginary magnet. So what should this look like? What pole will attract a north pole back? Awesome, the opposite pole, which yes, will be the south pole. Great, and over here we have the north pole. Great job. All right, now this time what happens if this is a south pole? How can we attract a south pole back? If a south pole is trying to walk away from us, how do we attract it back? We need a perfect. Regine, Sally, Antoine, Rowan, Greta in the chat box. I see you. Stephen, thank you for all that participation. Yeah, we're going to need a north pole. So a north pole will pull that south pole back. And over here, this is going to obviously be the south pole. Great job. Go ahead and give me a smiley face if that makes sense. This is literally what we did during our warm-up. So we should feel confident with this. The only thing we changed here is we added a loop. That's literally the only thing that changed. Great job, everybody. All right, let's go ahead and do number 2 and number 3 then in our assignment. So number 2 is that the magnet should be a south-north, so a south and north. And number 3 is that it should be a north-south. Go ahead and give me green checks when you have number 2 and number 3 saved. You have 40 seconds. Ready, set, go. What's up, Daniel? Number 2 is that it should be a south-north, just how you see it here. Yep. And then number 3 is that it should be a north-south. Yeah, so we filled them in, but this is how it's represented on your quiz. So as a south-north and then a north-south for number 3. All right, we're waiting on green checks, please. Brisa, how are you doing, Brisa? I haven't heard from you today. Let us know how you're doing. Brisa, green checks, please. Thank you. Waiting on Haley. And thank you, Haley. Perfect. Waiting on Jose and Luis. Jose and Luis for number 2 and number 3. Answers are up on the board. Easy peasy. Don't want to leave you behind. Oh, wow. Great job, Antoine. Yeah, you guys should be able to do number 4 and 5 if you've been doing the warm-up and following along with us. So if you want to try it ahead of time, go for it. Jose, Luis, green checks. Jose, Luis, green checks. All right, we'll go ahead and check in with you, Jose. And looking good. Let's go ahead and move on.
Inducing that magnetic field, but the magnet's like, oh, go away. So is the magnet attracting or repelling? Is the magnet attracting or repelling? That magnet is going in, and the loop is saying too close. What is it doing? Is it attracting or repelling? Yeah, good, excellent. Yes, Lisa's got an answer. Let's get some more answers up there. Yes, Antoine, Sally, yes, exactly. It's repelling it away. It's like, oh no, too close. So if that is saying too close, then what sort of magnetic field, what kind of pole would be right here in this area? Yeah, back up, yo. You're too close to me. Good. Regine's got an answer. Sally's got an answer. Beautiful. Yeah. Exactly. This would be a north. Remember, 2 like poles are going to repel each other, and then this would be a south, or in this end. Excellent job. All right, so let's go ahead and look at this one. If the south end of this pole is coming towards the this loop here, and the loop's going, oh no, back it up, yo, I do not want you near me. What would this pole be right here in this imaginary magnet? What would this pole be in this imaginary? Beautiful. Yep, I agree with all of you. Excellent job. This would be my south pole, while this end would be my north pole. So with that being said, excellent job. Let's go ahead and lock in our answers for number 4. And this is, I believe this is number 4 and 5, or just number 4. If not, let's go ahead. Oh, there you go. It is for number 4 and 5. You're going to lock in S and, or N and S, and then for number 5, S and N. We're going to give you 40 seconds to do that. There should be plenty of time to lock in your answers. 40 seconds. Give us green checks when you are finished. Go, go, go. Work quickly and promptly. Know that you're with us. Plenty of time to lock in our answers. So I'm going to go through Alec, green checks, please. Looking for Andres, green check, please. Andres, green check. And I'm looking for a green check from Lydia, green check. Lydia, green check. Andres, green check. Thank you, Andres. I saw that green check up. And Alec, thank you so much. Let's go ahead and move on. Excellent job, everybody. Nice work.
All right, so finally we get to the electricity part, okay? So everything we've done so far has been leading up to this idea that magnetism can create electricity. So electricity and magnetism are two sides of the same coin. So as soon as you get an induced magnetic field in our loop, that also creates an induced current. It creates electricity. So we end up with an induced current moving around our loop, moving through that wire, and that electricity can be used. So we'll see on Friday that we can actually use that electricity that is induced by a magnet. All right, now remember again that this is a plain loop of wire. It has no battery, no plug, nothing. The only reason it has electricity is from that moving magnet. From the moving magnet. So again, you can see that here we figured out what does the induced magnetic field look like. In this case, it's trying to repel a north that's trying to enter it, so it uses a north pole. And we're going to learn a right-hand rule in just a moment that then teaches us what does the induced current look like. Remember, current is represented with the letter I. This is number 6 in your assignment. Give me a green check when you have this saved. Fill in the blank with the word current. Does not need to be capitalized, but does need to be spelled correctly. 30 seconds. Go, go, go. Green checks. If we don't hear from you, we'll move you to the check-in room. 15 seconds remaining. Fill in the blank with the word current. Spell it correctly. Capitalization does not matter. Yes, you could spell it like that if you would like to. Alec. Luis. Green checks, please, for number 6. Alec. Green checks, please. You're my last one. Alec, hello. Are you there? Alec, green checks, please, for number 6. Alec, hello. Alec, green checks for number 6. Sorry, I'll go ahead and send your assignment. Looks like you came in a little bit late. All right, make sure we get your green check on the next question, though. Otherwise, we will check in with you in the check-in room. All right, let's go ahead and move on, everybody. All right, so now we're going to go ahead and learn our right-hand rule to learn what does this electricity even look like. So in both of our examples here, these are the first two that we started off with. We saw the magnet is leaving, and so the loop is going to try to attract it back, and that results in these induced magnetic fields that you see represented here. A south pole here to try to attract this magnet back, a north pole here to try to attract this magnet back. So what we're going to do is we're going to learn a new right-hand rule. And the way that you do the right-hand rule this time is you are going to point your thumb towards north for your loop. So the induced, the created magnetic field, not the actual magnet, but the pretend magnet. So point your thumb in the direction of the north pole of your loop. Once you do that, your fingers are going to show you the direction of the current. I find it's really helpful to hold a pen in your hand up to the screen because then you can figure out, are your fingers going up in the back or up in the front? That's what we're going to be looking at today. We're going to try to see, do our fingers go up in the back or up in the front for our current? All right, so I'm going to go ahead and show you what this looks like. Let me start my video here. All right, and let me fix my camera. All right, so taking a look here, we have a north pole. Our induced north pole in our loop is pointing to the right. So go ahead and point your right-hand thumb to the right. Okay, right-hand thumb to the right. Go ahead and do that and give me a smiley face in the chat box once you've done that. Go ahead and do that and give me a smiley face once you've done that. Perfect. Okay, so that being said, let's go ahead and take a look at this. If I go ahead and put a pen right here, which way are my fingers going up? Are they going up in the back or up in the front? Again, up in the back or up in the front? Up in the back or up in the front? Awesome. I see Sally. I see Lisa in the chat box. I see Rowan participating, Brisa participating. Where are the fingers going? Up and back or up in front? Or again, you can curl your fingers all the way around to see what your fingers do. Awesome. Yeah. So your fingers are actually going up in the back. So our current goes up in the back. And then our fingers curl down in front. Down in front. So here's our current. All right. Again, we can say that it's going up in the back and it's going down in front. So we are creating electricity, but the electricity has to go in a certain direction. So this is the direction in which it is going to move. Excellent. All right, let's go ahead and try this one. All right, so this time our north pole for our induced, our loops pretend magnet is going to the left. So point your finger to the left. If you need to, grab a pen. And this time tell me, where are your fingers going up? Are they going up in the back or up in the front? Where do they first start going up? Up in the back or up in the front? Go ahead and tell me in the chat box. Excellent. I see Sally, Lisa, Rowan participating. Let's get some more participation. Thank you, Jadelyn, Antoine. Again, I highly recommend do this yourself. All right, so your thumb is pointing in the direction of north for your induced magnet, your loops magnet, and then figure out, where do your fingers point up? Do they point up in the back or up in the front? Awesome, yeah, they're definitely pointing up in the front, right? So they first point up in the front. Once you curve over to the back, now they're pointing down. So that's definitely not going to be up in the back, that's up in the front. So taking a look here, let's go ahead and draw this out. So our current goes up in the front and down in the back. Remember, current is represented by a letter I. So over here, we're going to have up in front and down in back, down in the back. Great job. Go ahead and give me a football in the chat box if you feel comfortable with this so far. Football in the chat box if you feel comfortable with this so far. Great job, everybody. Awesome. All right, this is actually going to be number 7 and number 8. So again, what we saw here was that your fingers were pointing up behind the loop. And so when your thumb points north, your fingers point up behind the loop. So that's going up in the back, down in front. When the magnet is pointing to the left, your thumb is pointed to the left, and your fingers go up in front and then down and back. So this is number 7 and number 8. Green checks when you have these saved. You have 30 seconds. Ready, set, go. Daniel, the answers are already on the board. So we did this together, and now we're filling it out in our assignment. So again, if our thumb is pointing to the right, pointing towards north, here's north, so your thumb points towards north, then what you can see is that if you were to have a loop here, right, if you had a loop here, your hand would be going up behind the loop. So that shows you where the electricity travels. So it goes up in the back and then down in the front. Okay, same thing over here. All right, we point our thumbs towards north. And so this time, if we had a loop in our hand, we would see that the loop, our fingers go up in front of the loop. And then if we curve them, they're actually pointing down behind the loop. All right, green checks for number 7 and number 8. Waiting on Daniel, make sure I get that green check. Waiting on Isaiah. Thank you, Isaiah. Waiting on Haley, Ivana, and Jasmine. Haley, Ivana, and Jasmine. Thank you, Ivana. Green checks, please. Yeah, this guy has a broken thumb. Not really, but I couldn't find a good one that really showed it pointing directly to the right. But I figured you'd get it. Y'all are smart. I figured you'd understand. All right, let's go ahead and move on.
In that magnetic field, remember, we're going to use that right hand rule, so that means that we're going to put our thumb towards the north of the pretend magnet inside the loop, that pretend magnet inside our loop. So my thumb is going north into the pretend. I'm going to grab my pen just to kind of give this a way in which we can grab it and see. Am my hand going up and over the front and down the back? My hand going up and over the front and down the back, or is it going from back to front? Again, watch what I do. My hand is, here's my thumb pointing to the north of the imaginary magnet, up and front. What are we doing? Good, excellent, excellent. Yeah. Yeah, exactly. So that means you have to, yeah, so you have to, I mean, I can see if I can move my camera. Okay, so here is my computer. And so I'm going to go ahead and point my thumb here. I'm going to go up and over the loop, up and over the loop. So there's my long thumb pointing to that north right here, up and over. Excellent. All right, so that's going to be on that side. So I'm going to go ahead and just kind of do this one with you because I have my camera down at this point. So again, I'm looking for the north of my imaginary magnet. So again, I'm going to go ahead and find that north. It's going to be this way. So am I going up the back, down the front, or am I going front to the back? Back to front or front to back? Think. Again, you put your hand back to front. Good, good. The reason I'm going this one right here, number 2. So we're pointing towards the north on this one. So if I point north, again, my thumb is going to go north. Am I going the back up to the front? Or am I going, give me a, kind of confusing. Yeah, yes, yes, yes. We are going from back to front, okay, back to front. On this one, though, we are going from front to back, okay, front to back. Okay, again, this is, you have to go up to your computer screen to try it out, but we are going from front up in the front, down in the back, and then on this side, we're going from back, thank you, up in the back, down in the front. All right, so hopefully that's I know it's kind of confusing when I started moving my camera, but that is what we're going to be doing there. Let's go ahead and look at the answers here. So for number 9, again, here was my hand. Again, if you have to match it up with one on my computer, the thumb is going this way. It's going pointing towards north, pointing towards north. So that means it's going up the front and down the back. On the other hand, number 10 is my thumb is pointing toward the north here. Mr. Man with the broken thumb, he's going to be pointing to the north, and his hand's going to go from the back to the front. Once you go have that locked in, let me know by a green check. Go ahead and lock these answers 9 and 10 into your assignment and give me a green check. I'm already seeing some people submitting their assignments. Nice job, Greta. Nice job, Regine. Excellent. Excellent. Rowan, awesome. High five on that. Rowan, I just, I don't know if you've got my chat, but I did look into that glow-in-the-dark platypus. Super cool. Keep bringing those cool facts in. All right, this is number 9 and 10. 9 and 10, excellent. I think we're doing pretty good. I think the majority of us have turned it in. If you missed it, let's see, Alec, green check. Please give me a green check, even if you've already turned it in, so we know that you are with us. Alec, green check, please. Looking for a green check from Andres. Andres, green check. Greta, I know you turned it in. Go ahead and give me a green check. Haley, Isaiah A, give me a green check. Ivana, green check. Looking for a green check from Luis, Lydia, Madison. Excellent, Stephen. Excellent. Give me those green checks. Even though you have turned it in already, that just lets me know that you are with us. Madison and Lydia. Madison, Lydia, give me a green check. Looking for Ivana, Ivana, green check. Greta, Greta, green check. And finally, Alec, green check, please. Still missing a few people. Let's get those. Then you're going to have to go ahead and watch the recording. All right, let's go ahead. And I know a lot of you have already submitted your assignment. A lot of you have given us a shout out of what you got. Nice job. Super excited. Nice. All right, let's go ahead and take a look. We haven't asked you this question in a while. I'm going to go ahead and give your whiteboard tools. I want you to use your pointer tool and tell me where you land for Unit 5. How is your rate? I want you to rate your understanding for Unit 5. How are you feeling? Are you feeling awesome, pretty good, still need some help, or very confused? Unit 5 is just electricity and magnetism. Where do we fall? Where do we fall? So we're right in here. Okay, good, good. Some of us feeling awesome. Some of us still need help, and that's A-okay. That's A-okay. Excellent job. Excellent. I love it how we are feeling like we're in here. Good. Exactly where we would like you to be. All right, so let's go ahead and I'm going to shut your whiteboard tools off and talk about our prompt. at this time, our attendance prompt is when a magnet moves in and out of a loop. Remember, we're talking about in and out of the loop. This creates an induced what? What does it create? An induced what? Who knows the answer? Current, okay? Induced current. Remember what we talked about, that magnetism needs to have that magnet to go in and out to create that electricity. It just doesn't happen on its own. So make sure that you get that. This is the answer to your attendance prompt. I'm going to go ahead and give you your links for your attendance prompt. Please make sure we are ending class about a couple minutes early, so you're very lucky. Go ahead and make sure you get this attendance prompt in. Make sure you get this attendance prompt in. Make sure it's correct with the correct word of current.